Sound check.
Si vede o no?
Ok, sounds works.
So, I say I'm Gabriele Baldon, and thank you everyone for coming here today. Today I'm going to present my work, which is end-to-end convergence of an heterogeneous computing and networking system. So let's start with the scope of the thesis. So the scope of the thesis is to going towards an ubiquitous computing infrastructure. Why so? Because cloud computing is no longer enough. I mean, it has served us very well in the last, let's say, 10 years, but with new use cases such as robotics and autonomous vehicles that bring the convergence of information technologies and operational technologies, cloud computing is no longer enough. And also those use cases bring new KPIs, mostly related to latency, but also to privacy and security of computation that could not be met with cloud computing. So based on the scope of the thesis, three challenges were identified, are the one like depicted in this slide. So the first challenge is about virtualization adaptation, which is the adaptation of virtualization manager or virtualization infrastructure towards heterogeneous devices and networks. The second challenge is about fog-aware resource management, which is how we can effectively manage those heterogeneous and possibly decentralized and maybe also mobile resources that we can find in the cloud continuum. And the last challenge is about holistic abstraction. So given this abstract infrastructure that we can manage, given this API, or we can further simplify this infrastructure for application developer. Based on this presentation, also the thesis was divided in two parts. The first part that is about managing resources at the edge of the fog, and the second part that is about enabling cloud application via that programming. So let's start with the first part. In the first part, I'm going to introduce what are the difference between cloud, edge, and fog computing. What are the nowadays management solutions that we found at the edge or at the fog. Then we're going to see how we could observe this heterogeneity, and also we're going to see how cloud fog-aware the infrastructure management can enable new kind of application. So let's start with the first work. The first work is about cloud and edge management solution. So on the state of the art, we have several edge management solutions that are available nowadays. We will see that only few of them can perform edge-only deployments, and there is no experimental comparison again between those edge solution and the cloud solution that they are from. So the objective was to perform this. Objective is to see all those solutions perform in an edge environment, especially how they compare to the cloud solution that they are from. So the contribution was the architecture analysis of those edge and cloud solutions and the experimental evaluation on an edge-only scenario. And this addressed challenge fog-aware resource management. So, but let's start to what are the differences between the cloud, the edge, and the fog. Actually, as we can see from this slide, from this picture, there are actually a lot of differences, not only in the computing domain, because in the cloud we have like homogeneous data center with very large resources available, very well interconnected, in which the workloads are usually different layers of virtualization and calibration with data. While we go towards the edge, in this case, the telco edge, we have still, let's say, small data center, especially thanks to NFV, so we can do network virtualization. But the amount of data that is available is less. So we get aggregated data, say, between the metro ring or between a certain area, and then we start to see some heterogeneity on the computing device because we have more ruggedized devices that usually last longer compared to the one that we have on the cloud. While when we go towards the far edge or the fog, we see that the difference is even more different because we have a plethora of devices that are completely heterogeneous. Like we will have robots, we will have phones, we will have cars, and all this infrastructure actually could be leveraged to deploy services. But also from a network point of view, let's say the fog or the far edge, as depicted in this slide, is very different because we don't have like only wired connectivity or an homogeneous kind of connectivity, but we can have an integration of information technology, operational technology like CAN bus, Modbus, but we can also have wireless network, unreliable wireless network, and so on and so on. So given that this cloud of continuum, let's see what are the solutions that could be used to manage this. Actually, in this lab, in this work, we selected a few solutions, so the solutions that were available to complete their work, and we can see that only two of them could perform an edge-only deployment. So those are the ones that we selected. And actually, those two solutions derived from Kubernetes. So what we are going to do, we are going to evaluate those solutions and see how they compare how they behave compared to Kubernetes. But first, let's have a look at the architectural framework, at the architectural difference between those three edge management solutions, or management solution in general. So we have Kubernetes, which is kind of the de facto standard when it's about managing resources of the cloud, and we can see that from this slide that his architecture is quite centralized. So everything passes by the Kube API server, which acts like as a API gateway, and then there is aside of this Kube API server, an etcd, which is a storage used to store, let's say, source of true information about the infrastructure. On the data plane, we have the kubelet and the kube proxy that are actually two services that communicate with the Kube API server in order to deploy container and to perform networking configuration on the computer nodes. if you have a look at KFS, actually KFS came to be a lightweight Kubernetes, so maintain API compatibility with Kubernetes, but requires less resources. So what it actually does, it has the same kind of centralized architecture, but it actually squeezes all the components of the Kubernetes control plane inside a single binary, replace some of them and customize some of them, and replace the etcd with an SQL-like database. And same thing it happens on the data plane, so it's squashed together kubelet and kubeproxy to have a single binary. Then we have KubeEdge, and KubeEdge, if we remember the previous slide, there was a little star when it's about edge-only deployment, and we can see why on this slide, because the cloud core, which is the control plane component of KubeEdge, always needs to maybe communicate with a Kube API server. So technically, if you have a Kubernetes running at the edge, this could be an edge-only deployment, but most of the time, this deployment will maybe not be edge, because maybe connect to a Kubernetes API in the cloud. And on the data plane, it's very similar to K3S. There is this edge hub, which is single binary that scores together the responsibility of kubelet and kubeproxy. And you also provide some device abstraction from a very well-known device to be exposed to the application. So all we want to evaluate is, we have this resolution, and we want to evaluate all the API patterns. And as metrics, we took the service instantiation time, with the RAM utilization in the controller node, and the network utilization, again, between the controller node and the compute nodes. So in order to evaluate the service instantiation time, we define a matrix, which is the deployment factor, so the one, this one, which is the time needed to deploy X services per node with Y nodes, divided by the time needed to deploy one service per node with 10 nodes. Similar thing was done for the RAM utilization, so we defined this metric, which is the load factor, in which we have the RAM utilization on the controller node with X containers per node and Y nodes, divided by the, let's say, the compute nodes at the controller node at idle, so we have zero services running and 10 compute nodes connected. We selected an application that is representative of kind of an edge application providing a REST API, so an API, an NGX server, and we provision the image beforehand in order to not impact the service instantiation time. Then we had some script in order to be able to automatically increase the number of connected nodes from 10 to 100, and also the number of containers per node from 1 to 10. So we go from as little as 10 services running on the edge infrastructure up to 1,000. This gives us a rough idea on how many resources are needed to have this workload running at the edge. Let's start have a look at the experimental result. So let's start with the results on network utilization. So as we can see from the graph, we have actually two different, I don't know if they play well on the screen, but we have two different graphs. Well, the same graph, we have two different, the metrics in two different cases. In the case, so the dotted one, in which we have the number of the kilobytes needed per each node connected to the controller node, while with the strict one, we have the amount of network utilization of the kilobytes needed per container. And actually, from this graph, we can see that the amount of network required is dominated by information coming from the infrastructure, not actually from the workload. Why so? Because the schedule is to be informed about what is happening on the infrastructure in order to deploy the services. So there is actually a constant stream of data going from the compute nodes to the controller node. And as a bit on the slide, it's very important to keep in mind that this data is always pushed to the master. So it's not like the controller node or the master node is getting this information only when it's needed, but this data there is a constant stream of data, which actually may not be very good when having mobile devices or mobile infrastructure, or the infrastructure that could have intermittent connectivity. Next, let's have a look at the experimental result about the time needed to deploy the services. So if we see the Kubernetes and KFS, we can actually see that the behavior is very similar. So the more nodes you have, the more time is required, but also the more containers you have, the more services you have, the more time is required to perform the deployment. This is very easy to explain because there are more nodes, so the schedule has to go through all of them in order to find the one where we can deploy, and also to avoid to overload just few nodes of the infrastructure, kind of an even distribution of the services. Same thing for the containers. So if we ask, in the case of 10 containers per node with 20 nodes, actually there will be 200 services that needs to be deployed, and what the scheduler does is paste this schedule in order to avoid to overload the nodes. And actually we see that the behavior is similar, but the number in general are different in Kubernetes and KFS. And this shows that actually for the initial part of the graph, KFS, let's say, only one approach pays well because there is less network overhead and less communication that is needed between the microservices. But then when we go to the extreme, so with 1,000 services, the fact of accessing this SQL database that is in file actually introduce a bit more latency compared to Kubernetes, where everything is in memory. What the KubeEdge on the other side has a behavior that is completely different. In the case of KubeEdge, actually what happens is that let's say with 10 nodes and 10 containers per node, so with 100 services running, what KubeEdge does, it wrongly reports information to the Kubernetes API, so the schedule is not able to pace the deployment. And so the deployment goes all to the same node or to a set of small nodes, to a set of those nodes, and they arrive all at the same time. So this has a huge impact on the deployment time, because actually the node is overloaded trying to continuously spawn containers. That's the impact actually, and we can see that the way KubeEdge actually works, or the schedule of KubeEdge works, and the way it reports information to Kubernetes is not smart compared to the other two. Okay, let's go to the next slide. So let's now have a look on the experimental evaluation on memory utilization for Kubernetes, KPS, and KubeEdge. As we can see here, also the behavior for both Kubernetes and KPS is similar. It's slightly different than before in the sense that also in this case, the amount of memory required is dominated by infrastructure information, not by container information. So indeed, that's why we can see on the x-axis, it increases, but increases not at the same rate when it increases on the y, compared to what it increases on the y-axis. That's because, as was happening also for the monitoring, infrastructure information dominates the amount of information that is needed to be kept in the container. And actually we see that the same behavior happens for KPS and Kubernetes. In this case, you can see that the being lightweight for KPS is actually true, because the amount of RAM increases is actually half compared to Kubernetes. While in the case of KPS, there is no actual impact, or there is very less impact compared to the other two solutions. And this is because of this architecture. So actually it's connected always to a Kubernetes API server, so actually information about infrastructure are always be stored in Kubernetes. KubeEdge just keeps a little information about what are the device abstraction need to be exposed and what are the nodes where it's running, but it doesn't keep information about the actual, doesn't keep actual information about what there is inside those nodes. So summarizing, we can see that information stored in the controller, information streamed to the controllers is always dominated by information coming from the infrastructure, so no information coming from the workload. We can also see that the scheduler needs a constant stream of information in order to do an informed decision when deploy the nodes. And also, all the solutions that we evaluate in this case, they can only manage containers. They do not manage VM, they do not manage native application. So this is kind of a limitation, because if we see this cloud thinking infrastructure, we cannot think to deploy a container inside a car. Maybe we could, but it's the right solution, or even on a fork or on a single board computer or something that is very small. So with this solution, we are only limited to container, but maybe we need something that is able to deploy different kind of workloads on the different types of the infrastructure. Now let's have a look at the second work for this part, which is about multi-tier orchestration in the edge flow. So we depart from the state of the art, in which we have NFV orchestrator that exists, but they are not yet integrated with edge and MEC domain, and also from the challenge identified by Etsy about NFV and MEC integration. The objective is to see all those solutions, all MEC and NFV could be efficiently integrated, and the contribution is the design implementation of a fault and ledge-aware NIM solution that is going to be used in the evaluation, the implementation of plugins for MEC and the integration with the multi-tier orchestrator, and the evaluation of this solution in a temporary scenario. But what is a multi-tier orchestrator? So a multi-tier orchestrator is a way to actually abstract the difference on the different domains of the infrastructure by providing an abstracted API that unifies them. So actually the MTO provides a unified view of the cloud, the edge, and the fog domains to its user. That could be, as in this slide, an end-to-end slice manager, an SSBSS, so user directly using the API from the infrastructure. And also can simplify the integration between NFV and MEC, because he understands both, let's say, information model, and is able to trigger the right orchestrator at the right time. And this also allows for better resource utilization by splitting the responsibility. So we have the MTO that actually does the, say, as a passing papers job, let's say, and organizing the calls between the different orchestrators. But the different orchestrator doesn't need to know the different information model, doesn't need to do more job compared to the one that they usually do. So, but what are those challenges that there are in NFV and MEC integration? I just list like 3 of them. I think they're one of the most important ones. First one is about communication between the mobile edge application orchestrator and the network report function orchestrator via the MD1 reference point. So In the case we want to integrate, let's say, both of them without an MTO, means that one of the two needs to understand both information models. So it needs to understand the MEC information model and the NFV information model, which means that yes, actually cannot be off the shelf. We need to take something, update, modify it in order to support this kind of deployment. While with the MTO, we could just take off-the-shelf orchestrators for the different domains. We could take like Kubernetes for the cloud, like OSM for the NFV, we could take, in this case was Photo5 for the edge, and we just can use them without needing to update, to modify them. The other challenge was about the integration between MEC and NFV packages, because the NFV package contains information about how to deploy the service. The MEC package could contain this kind of information, but it also takes information about the service that is going to be deployed, because MEC service is going to be provided to user connected to the MEC deployment. So the MTO has access actually to both catalogs. Those catalogs are separate and external, and the MTO is able to keep reference between those two packages. So we could have the MEC app that only reference the VNF app in the case it needs to deploy actually something on the NFVBI, or in the case it's a service that it provides directly, but the MEC platform doesn't need to do so. And also the MTO can forward the right part to the right orchestrator. Similar approaches when it's about onboarding the application, so actually deploy them. As those catalogs as external, the MTO can only trigger the responsible orchestrator without needing to crosstalk between the orchestrators. But let's have a look at the result that we had in the evaluation. So we have the three different approaches that could be used. So the MTO base, which is the proposed one, the NFVBO master base, and the mobile application orchestrator master base. So what we see in this graph is the, let's say, the simplified call flow between the different scenarios. So in the case the MTO is a master, the MTO base receives the generic service deployment request, and then is able to call either the NFV orchestrator and the MEC orchestrator based on the service request. And on the case of where the NFVO is a master, we have this still generic service deployment request that arrives, and then the NFVO actually to call itself to deploy the service and then call the MEC orchestrator. While in the case the mobile orchestrator is the master, the situation is similar. So the mobile application orchestrator has to first call the NFVO to deploy the virtual network functions, then call itself to deploy the service in the MEC. So in order to avoid the resource utilization, we take the maximum CPU load on the different scenarios for the NFVO and for the mobile application orchestrator, and we increase the number of concurrent instantiated services. So as we can see from the first graph, that is kind of our baseline with the MTO, in which we can see that it grows linearly for the NFVO when it's time to deploy service, while the mobile application orchestrator is not that much impacted. On the second graph, we can see actually in the case where the NFVO is a master, that the resource utilization on the NFVO actually increases significantly, and we will see that already where with one service is around 10%, and it still grows with more services to be deployed, while the MTO, the mobile application orchestrator is actually not impacted because it's doing the same job as before. It's not like instantiating new services. A similar behavior we could see with the case where the mobile application orchestrator is a master, because in this case you see the NFVO actually resource utilization is similar to the first case, it's actually doing the same job, while the mobile application orchestrator resource utilization increases a lot. This shows that actually if we have, with an MTO approach, we could have better resource utilization because the MTO could take care of actually calling the different orchestrator, and keep in mind that those orchestrators usually run on edge devices or on edge infrastructure where the amount of resources is not like infinite. So it's important to keep in mind that if, for instance, we take the case of the NFVO as a master, we're using more resources administrative domains, so you need to be able to federate resources between those administrative domains. So the objective is how can context-aware resource management improve robotic application, and the contribution is the integration of this context-aware information to enhance edge robotic application, actually take smarter decision on the infrastructure, and also the integration and evaluation of federation mechanism in the context of resource sharing. And this addresses the challenge on virtualization adaptation and fog-aware resource management. But what is fog-aware resource management? So in fog computing, as one of the first slides I presented, we have this access to context information, because those information are closer to the computing device, so we could access them. So why we cannot leverage them to perform a smarter application deployment? So why we cannot leverage them to decide, for instance, where to deploy a virtual access point, or where to scale up or scale down, for instance, other network services, because we have more users. But so as we have those edge resources, we can use them to deploy on-demand network services to enhance applications. In this case was the deployment of network infrastructure to support robotic application. And also the scope was to validate this fog-aware infrastructure manager with real-world application, not just with the let's say, use case that we did before. So what we had a test bed here in C3M, actually in the hallway of the, I think it was this floor, which had different compute nodes that were connected through and were running under the same orchestrator or different orchestrator events on the true use case. And on those nodes, we deployed our own virtual infrastructure manager, so the one developed for the previous work, and we enhanced it with getting access to context information and to expose, in this case, was a robotic application. So what we actually did was an end-to-end robotic system. This end-to-end robotic system is actually composed by 3 different components, 3 different subsystems. So we have the robotic system, which we have everything that is related to robots, so the sensor, the actuators, the brain of the robot, so the control movement of the robot. Then we have the edge info computing system, which actually is the infrastructure, so where we have the virtualization infrastructure, we have the MEC platform, and we have the services that are going to be exposed to the MEC platform, which in this case we have radio network information and organization service. And we have the third subsystem, which is the orchestrator subsystem, which you have the orchestrator and the virtual infrastructure manager. So the first integration that we did was to get this context information and use them to perform a smarter deployment of network services for supporting a use case. In this case, in the hallway, we had these 3 compute nodes that were all under the same administrative domain for this use case. And we had, in one node, we started a virtual access point. Then we had another node in which we were running the orchestrator and also say the brain of the robot, so the part that decides where the robot has to go. And then we had a third computer node that at the beginning they were not deployed on those nodes. So what we did, the robot was starting from point A at 0.2 meters per second. And from the orchestrator, we were monitoring the signal strength and also the amount of retries on the radio link. So as the robot starts to move, in this case, when it did around 7 meters, we get from this radio network information service that the signal strength was starting to lower. Still, the amount of retries was acceptable, was under our threshold, but we did okay. In this case, the algorithm was okay. Let's start to deploy this virtual access point. That this actually happens in point 1 on the second graph. So there we started the access point. So the virtual infrastructure manager started the access point in around 3.7. So the robot did another 0.7 meter. At point 2, the access point was deployed, but was still not, let's say, so the access point of the container was available, but the access point was not yet discovered by the radio network information service. This actually happens a few meters before, in the vertical line around the 3.6 meters, so it was around like 9-something meters. From that point on, we see that from the radio network information service, we see that we are getting information about this new access point. Up to a certain level, then the robot of course continues to move. At point 3, we detect that actually the retries for the first access point were above the threshold for some time. So we decided, okay, at this point we are going to destroy the first access point and the robot will connect to the second one. So at point 3, actually, which is similar more or less to the point B in the map, the first access point was teared down and the robot connected to the second access point. In total, the radio link downtime was around 36 milliseconds, which is less than 1 centimeter at the speed the robot was doing, which is acceptable. So the robot wasn't without connectivity for a long time. And actually the tear down of the access point took another 3.5 seconds. And so after the, let's say, the green mark, there were no more first access point, the robot continued to move this journey to point C. The second integration that we did was with, as I said, federation mechanism. So why so? In the edge infrastructure, you can cross more administrative domain compared to when your application is only deployed on the cloud. So the idea there is, if I have a robot that needs to deliver some goods from, let's say, inside the city, from point A to point B, most probably it's not going to be under the same administrative domain for all of the journey. So it's important to see what is the impact of the federation on the deployment time, and what is the impact of the federation on the federation procedure, and how much of this impact is related to the deployment time. So we actually did a breakdown of the federation procedure, and as we can see from this slide, we can see that 2/3 of the time are used by choosing what is the second domain where we're going to deploy, so what is the federated domain is going to deploy the network services, and 1/3 is taken by actually the deployment of the service on the second unrestricted domain. And actually, we did a breakdown of all the steps, and we could see that the deployment time per se is still 3.5 seconds, so it's compatible with the dynamic of the system. Most of the time is taken by the actual start of the access point on the radio link, which takes, in this case, still around 3 seconds. So from this, we could see that actually the design beam solution was compatible with robotics application. It's also compatible with the time frame of the robotic application, and it allows to integrate context information, giving both them to the application or to the orchestrator in order to facilitate the deployment. So concluding part one, let's summarize what we have seen. We have seen how nowadays cloud and edge management solution deals with an edge infrastructure. So we evaluate them, and we have seen also to integrate a fog-aware beam with existing NFV and NFV deployment, and we further evaluate this fog-aware BIM with a context-aware self-deployment in the context of robotic application and also in the context of federation of services still for robotic applications. So those are the contribution to part one. Let's now delve into part two. So part one, the objective was to try to abstract this infrastructure. So let's imagine now this infrastructure is completely abstracted, so we are able to deploy those services from the cloud to the thing without bothering where they are actually running, without actually needing to configure all the infrastructure to deploy things in the right place by ourselves. And we have this unified API. But that's still not enough for application developers, because they are lazy, so they don't want to deal with configuration of endpoints, they want to deal with networking configuration, and actually most of the time they don't even understand in the complexity of the cloud to thing continuum how to interconnect things. So the idea is how we can further abstract this cloud to thing continuum to application developers, and can a data flow based programming model facilitate cloud to thing applications? But first, what is a cloud to thing application? So a cloud to thing application, as the name says, is an application that has components that span from the cloud to the edge up to the devices. So this application, as the one depicted in the slide, could be quite complex. So as an application developer, I don't want to configure each component, where it's running, how to connect, how to communicate with the other components, and most of the time, maybe I have not even idea of how to configure it, or I don't have access to the configuration of those, let's say, of the endpoints, or to the, let's say, SLA and all this kind of stuff. So how I can do it. So the idea is that we should empower developers to leverage on this infrastructure, and all the configuration should be taken into account by a framework. But as you're developing a cloud to thing infrastructure, and you don't want to deal with endpoints configuration, you don't want to deal with maybe security configuration or deployment, few concepts becomes important, like location transparency, because I don't need to actually know where the components are going to be deployed, just want to deploy them. But also data centricity, because I don't need to be off-centric anymore. I don't want to be off-centric, because I don't want to know that, for instance, the component about scene perception is running at the edge of that specific IP address. I'm just interested on the data it's producing. The other components are interested on the data I'm producing. So the idea there is actually to completely abstract the infrastructure and just provide a programming model for the users, so that for the developers in this case, a way that they could just simplify all of this. So what we actually did was taking these, let's say, requirements. So developers must be able to leverage on the infrastructure. They don't need to know where actually the code is running. They could give hints like, I need this component to run with a GPU and this component to run with a TPU. Fine, but you don't need to know actually where it's running. Same, again, the API has to abstract all this complexity. So I don't need to know that I need to create a virtual link between those two components, then I need to create an overlay network between these two, and then I need to create, I don't know, a VPN because this is a public address, and so on and so on. The idea is that the API must abstract such complexity. And we also need the possibility to run different instances of the same application, either on the same node, either on different nodes, without actually having crosstalk. So we can now way to achieve multi-tenancy. So now if we take a look at let's say from the developer point of view, what actually I would like to do as a developer, because I'm lazy, I don't care about the infrastructure, I don't know what the actual infrastructure. I want just to define how my application is going to, let's say the graph of the data that's going to flow on my application. I want to define the data flow on my application. I want to implement the components that compose my application, or may also reuse components that already exist, similar to what happens today with Docker. Let's say I have a component that does perception, maybe I want to reuse it. I don't want to develop my own. I just need to connect them. once I define, let's say, my application and the way it communicates and the different nodes and implement them, I just want to abort this descriptor and the binaries to this framework. And this framework, of course, is going to store them in a kind of distributed registry in order to have access from anywhere on the infrastructure. And then at the second time, let's say in a synchronous time, I could decide to then, okay, fine, now I want to deploy this actual application. When it's time to deploy, then this framework has to schedule the components on the right node based on the hints that were given in the descriptor, if there were any, configure all the underlying connectivity, and run the application, which means in this case also avoiding crosstalk, so create like isolated link for the different application running. So let's say that we developed actually this data flow framework on top of data-centric middleware. So we decided now to evaluate it. So first evaluation that we want to do is, can this framework enable cloud-to-fin federated learning? Why we choose federated learning? Because it's something that for the time is mostly happening on the cloud. So it's not that. There are few cases in which it's happening on the edge, but you don't have actually cloud-to-fin federated learning for the time being. So instead of the we have this MLOps pipeline that we are going to see what they are in the next slide. We have those data-centric middleware that actually exist, but so far have never been used for MLOps. And we have this data flow programming that could simplify pipeline definition, so could simplify the definition of the application. The objective is to see if this data flow and data-centric framework could be used for MLOps, what are actually the impacts, and the contributions there, the design implementation, that is the one that actually we have already seen, the port of an existing MLOps pipeline, this data flow paradigm and data-centric paradigm, and run it be able to run it across the cloud-to-fin continuum, and the evaluation this MLOps scenario. So this addresses the challenge of holistic abstraction, and actually this framework has been used in the Daemon and ICOS project. But what is an MLOps pipeline? So as the name says, it's actually a pipeline, so different steps run one right after the other, and those steps are usually 5. So first one is data collection, which is getting the data from sensor, from the internet, scraping the web, and so on and so on, depends actually the use case. Then this data is going to be transformed in a standardized format in order to be used for training. Then there is the training step, in which part of this data is given to the model training up to a certain, let's say, accuracy is achieved, and then the model is evaluated with known data to actually verify that the threshold was achieved, and then this model gets deployed. So this is actually a pipeline, and if we think of data flow that defines application as a graph, pipeline is just a simplified graph, because everything is just connected straight one after the other. So what we did is, okay, we have this framework that is called the Xenoflow, that is data-centric, peer-to-peer broker, and so on, and that can support this counterfeit deployment. And we did qualitative analysis or other data-centric framework that could be used to achieve the same result. So we took a look at MQTT, we took a look at Kafka and Co. At the end, for the evaluation, we just selected the Pro solution and MQTT because are the only one that can actually perform cloud-to-fins deployment, while Kafka is mostly used on the cloud and Co is mostly used, let's say, on the field side per se. So what we did, we took the pipeline. This case was a pipeline getting data from few houses in Portugal, from data coming from like home comfort, like temperature inside the house, presence sensor, and this kind of data. And this pipeline, we have actually six models being trained at the same time. And we can already see from the, let's say, architecture of this pipeline that they are quite different when using QTT and when using the Pogo solution. Because in the case of QTT, as I said, it's a brokered, has a brokered approach, which means this broker has to be reachable by all the nodes. So could be placed in the cloud. In the case this is a cloud-to-fin deployment, because otherwise things will not be able to reach it. If we place it like, so if you place it like at the thing side, then from the cloud we cannot reach it, then the way around. So this means that there will always be like one additional hop between the different components. While in the case of the Pro solution, we can actually define in the data flow descriptor this pipeline, and we get, of course, automatic, let's say, multicasting in the case we want to train more things at the same time. And this is simplifying, and we don't need to have more additional hops. Another, let's say, advantage of the Pro solution is that in the case of MQTT, if I want to run more deployments of this thing, so if I want to have like data from different houses not have crosstalk, I need to define the topic name manually, and this is error prone as a developer. Because if I misspell one of the name or the, let's say, topic names, or I misconfigure them, all of a sudden it will have crosstalk between different pipelines running, and this has an impact on the data. While in the case of the Pro solution, all of this, all the network configuration, topic name configuration, is done by the framework per se, and it ensures that there are no crosstalk. Plus, the framework is also able to do optimization in the case things are running on the same network, or they're running on the same node, or even on the same process, in order to avoid copies and to avoid serialization when it's possible, so to improve the performance. But actually, all these things performs compared to, in this case, it was MQTT. So what we did, we measured the latency between the different components on the pipeline, and so only the network latency in this case, and we could see that actually the proposed solution has a better distribution of the samples in this case, so that 99% percentile is between 50 and 100 microseconds, while in the case of MQTT, we have seen this very strange step distribution, and actually the maximum goes up to 1 millisecond. So it's very difficult to actually try to understand how many latency you're going to get by using this case MQTT. This is kind of expected because is using a broker, if more data is, as the pipeline goes through, the data is going through the broker, multiple data can arrive the broker at the same time, which is, of course, will introduce latency because the broker has to elaborate on this data at different times. Well, they're at the same time, so he has to paste them. Then we did, okay, we have this approach, so this actually shows that the data flow and data centric approach could be used for MLOps. We actually evaluate that the proposed design doesn't add an impact on performance, even if using a higher level of abstraction, and means that you can actually get a cloud thing deployment for MLOps without paying the cost of sending everything to the cloud in the case it's not needed. We want also to further evaluate this framework, by this case taking, let's say, a telco-related use case. So what we did this work called data-centric approach for edge native 6G SBA. We departed from the 5G SBA, which is still host-centric, because services need to know where the other are. And there is this cloud thing continuum. And the objective is how can data flow and data-centric framework improve future 6G SBA. So the contribution is the design layer for 6G SBA, a POC implementation of some of its component, and the evaluation of the host solution. So what is the SBA? The SBA is the service-based architecture, which is the core network actually of the 5G network. And at first, you have just point-to-point communication between the different components. Then after some time, 5GPP decided to use the method everything by gateway, so kind of get rid of host centricity, but you still need to know the gateway and the gateway, the SCP, so the service communication proxy. And it also needs to know where all the other services are. And this, of course, introduces latency because now I have one model. But as written in the slide, this is still host-centric because I need to know where the actual services are. So I need to do a call, in this case, to the network registry function to see if those services are available, what is their address. But what if I want to run some of those services closer to the user so they can know? So in a way that, say, they are not directly reachable by IP addresses or by domain names. What will do that? So the idea is apply data centricity to the SBA in a way to get location transparency and also the inclusion for fog and edge resources. So what we did, we designed a layered approach, we designed a layered architecture for the 6G XBA, sorry. We focused only on the control plane part, so we left untouched for the user plane part, although the same approach could be taken on the user plane, data plane. So what we did, we defined this layer architecture that has actually 4 layers. The first layer, the service data flow layer, is the layer where you define actually the procedure. So say session stub mesh, policy management, and so on and so on. So at this layer, you define the service flow, so which function is to send data to which other function in order to achieve a certain result, in this case, for example, a certain procedure. And this layer is location transparent because each component doesn't need to know where the actual other components are running. And this deployment transparent in the sense that the same instance of the function could be used across different procedures. Then this layer configures the underlay layer, which is the data-centric routing layer, which is used to actually route named data across the infrastructure. So this layer takes care of, based on the configuration that is receiving from the service data flow layer, to route data between the different atomic functions, in this case, say function 1, function 2, and so on and so on. Above this layer, we see the, above, let's say, on the graph, but technically is more or less, below, but technically is above. We have the same atomic function instance. Those are actually the business code. So in the case of 6G SBA, those could be like part implementation of atomic functions that do that. So in 5G SBA, actually the functions are not per se microservices. They're quite big services. So the idea here is to actually decompose those services in more simplified and serverless and stateless, hopefully, microservices that then will be connected by the data-centric routing. So those atomic functions are actually atomic in the sense that they do one job, or they do like a very small set of jobs, and they do it well. So they're actually microservices compared to services as we have nowadays in the SPA. So those atomic functions are instances on top of the distributed resources that are actually the one that we seen on the first part of my presentation. And they actually reduce data interest on the data-centric routing. So the idea there is to, with this approach, is to simplify a few things, like having a more efficient core network scenario, because I don't need actually to, the procedure is defined in a descriptor, so I don't need to look all the document to understand which call I need to do all the time, but I could just define on a file, okay, look, this is the procedure that we need to do for the PDU session established, and can only be that. I cannot do mistake on that procedure. When I deploy, I actually deploy that procedure in the service data flow layer that then takes care of configuring the DCN routing, and the DCN routing will forward the data only to the right functions. This also allows, of course, for streamlined refactoring, as in the case I want to change one procedure, I can just change the script of this procedure without maybe needing to have an impact on the services, because those services are atomic. I could decompose them in a different way, I could arrange them to achieve the same result in a different way or to achieve different results. This also enforces the use of serverless, stateless, and shareable function. Shareable in a sense that, as I said, I can use the same instance across different service definition, but also if those same functions are stateless, they could be like turned off and on without bothering about their state. So they could scale up and scale out to go way more easily compared to scaling up and scale down something that is stateful. Serverless, although it's kind of, I would say, abuse word, is because it's always a server, is in the sense that those functions could be, let's say, activated only when it's needed. Which, for instance, let's take the case of the session management. If F1 is sending some data to F8 and there is not yet an instance of F8, and maybe it's not needed after, I could just start this function on demand, processing it, get the data out, and tear down it if I don't need it. As it's data-centric, we could also leverage, in this case, we could get infrastructure that is all across the continuum, because the data-centric routing is location transparent, so it's able to route data no matter where the actual endpoints are. And also we could get different, security could be addressed at different levels. So like the DCN routing layer is able to get security, let's say, on point-to-point basis, so like having MTLS and TLS communication between the actual function, while the session management, the service data flow layer could provide end-to-end security. But okay, sounds fine, but what are the actual results? So what we did, we implemented part of this layered architecture with different protocols, and actually selected 5 different protocols to evaluate against the proposed solution, which are HTTP, gRPC, and Istio for the request reply part, because there are procedures that require a request reply approach and those that require a publish subscribe approach. So we took these 3 for the request reply, and we took Kafka and MQTT for the publish subscribe part of it. So HTTP with flag is actually the de facto standard, so it's how the 5G SBA is defined. gRPC is widely used on this kind of microservices and service-based architecture. Istio is actually the state of the art when it's about service mesh. So things running on the same cluster without actually needing to be to know where the services are running, because it's kind of data-centric, say more service-centric. While for the public subscribe part with Kafka, because it's widely used on the cloud to get for this kind of for, let's say, money for notification and this kind of stuff, and MQTT, because also the facto standard is about protocols that are being used in a public subscribe base. So what we implemented like 5 components of the SBA, so EMF, SMF, UDM, and NRF and PCF. And we selected 2 different procedures. One that is more request reply, which is the PDU session establishment, which are 5 request reply calls, or 3 in the case we don't need the service discovery, also we don't need the copy on NRF. And then we also select the charging policy update as the publish subscribe procedure. So session establish is establishing the data path when the user feedback connects to the 5G core and establishing the data path, while the charging policy update is about how I should charge the user for the data transfer. So after we implemented, we actually did some evaluation, and what we could see actually from this graph is that we did both service discovery and non-service discovery, because in the case of data-centric and service-centric, there is not actually to perform the service discovery part, but we could argue also that in the case of HTTP and gRPC, you will just do the first time you need to find the service. And here we could see that actually there is very similar performance between gRPC and HTTP. It's quite easy to explain. They are both based, well, gRPC is based on HTTP too, but it enables compression and uses protobuf as a serialization format, which is more, let's say, more efficient compared to JSON, so that's why it's a bit less, but still they are on the same, let's say, the same bucket, so they are very similar. What we were a bit surprised was Istio, because it's kind of the de facto standard in service mesh, so everyone uses them on the cloud inside Kubernetes cluster. But so Istio is, as we say, service-based, service-centric. So what he actually does, each service has a sidecar, say, application router, so level 7 router, that routes the information to the other service. So this means that there are actually always two ops between one service and the other. This explains why the performance are, say, worse compared to the others. While the Pro solution actually is always is at least one order of magnitude, but a bit less than one order of magnitude better than the others. And this is because, as I said, the service-centric routing is very efficient. We don't need to perform the service discovery, and even in the case we need to perform it, it's faster. And also serialization is way better compared to the one used for your solution. Then we did the same. We repeated the same evaluation, also with the pub sub scenarios with the charging policy update. And here, as we can see, Kafka is the one that performs worse compared to, say, MQTT and the Pro solution. Actually, 2 order of magnitude higher most of the Pro solution. And why so? So Kafka is actually being designed to be used on the cloud. And it's designed in a way that is pool-based, which means that when I publish the data, the subscriber is not notified. It needs to go fetching the data to the server. This, of course, means that if we are publishing fast and we are getting data fast from the server gets overloaded. And that's why it, of course, has a very high impact on the latency. That's actually what was happening there. MQTT, on the other side, it doesn't perform, let's say, bad in general numbers, but it outperformed the Pro solution, mostly because of this centralized architecture. So data has always to go through the broker, which is not the case in the case of the Pro solution, where data can flow directly between the 2 different services inside the SBA. But okay, our performance is the only thing that matters. I would say no, because our objective was to simplify the job of developers. So part of the results that we have just seen could be explained because the Pro solution has a lower overhead compared to the other one. So as we can see in the case of big usage establishment, the overhead of the Pro solution is around 9%, while it goes up to 63% for gRPC. And similarly, in the case of the charging policy update, so the overhead of the Pro solution is 20%, while the overhead of the Kafka is 22%, which is huge, and QT is 65%. But in this case, we are interested in simplify the life of developers, which means we want them to write less code. So in the last line of actually this table, we could see that we did the line of codes that were written in order to implement those services in each of the solutions. So we could see that actually the Pro solution is like 4 times lower than HTTP, so we need to write four times less code, which means less bug that I'm going to introduce, and then I don't need to actually think about line of code that I don't need to write, and 5 times less than Istio. It is more or less in the same bucket as gRPC. That's why actually gRPC is widely used, but still it's 138 line of code less, which means that actually our objective to simplify the life of developers is true, because they need to write less code. In the case of the charging policy update, there is, let's say, not the same amount of difference between the PQ session established, and we also need to report that there are less calling calls per step. And we can see that the Pro solution and QTT are actually 20 lines of code difference. But keep in mind that in QTT I need to define the topic name, so if I misspell a topic name or misconfigure it, I could have crosstalk between things, which is something a developer would not like. But Kafka actually requires like almost double the amount of line of code for not good performance in this case. So concluding part 2, we have seen that this data-fluent data-centric middleware could actually be used for MLOps and XGSBA, and actually it doesn't, although it has a higher level of abstraction compared to let's say normal HTTP or MQTT, it doesn't. This high level of abstraction doesn't reflect on the performance and actually simplifies the amount of code that needs to be written by the developers. So they could get less code and better performance, which I think is good. So those are the contribution to part 2. So let's take a look at the conclusion, so some takeaway and future direction. So let's say start from the takeaway. So you see that state-of-the-art orchestrators, especially the ones that were designed for with the edge in mind, do not sit the continuum. Why? Because they're centralized. So what if I cannot reach the control node for some reason? So logical single point of failure, and requires always some connectivity when in general streaming data it gets information about the infrastructure, and there is no leveraging context information that are actually available at default or at the edge. So we need to have this unified abstraction across the continuum. So we need to have this heterogeneous could be abstracted for application developer or in general for everyone who needs to deploy this application in order to simplify this. And we can also provide context information either to the orchestrator or to the application developers in order to enhance their application. But it's not enough because establishing the heterogeneity of the infrastructure is one step, but still developers would say they do not know how to configure the infrastructure most of the time. So we need still to further abstract this in order to simplify their work. So what we did, we designed this data-centric based data flow framework that helps developers focus on their business logic, and you'll see that they can get good performance writing less code. But there are still, this is still not enough, there are still things that need to be done. So what are the future direction? On the, let's say, identified free, let's say, access. So on the orchestration side is, we need algorithms that are able to actually deal with the heterogeneity that does not come only computer networking, storage, but also come with volatility and possibly mobility of resources where things need to be deployed. So in the case the car is part of the infrastructure, this has to be taken into account by the orchestrator because maybe it needs to deploy service there that makes sense. You cannot deploy a VNF inside the car that then moves, which makes no sense. And also these algorithms should leverage on context information because as we have seen, this could enhance application like in the case we have seen with robotics. But new framework that come, they still need to support existing frameworks because there is, everyone would like to work on a greenfield deployment, but we know that brownfield deployments are a thing. Actually, most of the things that need to deploy on systems that are already working. So there is, as written design, no one size fits them all when it's come to deployment. So let's say only containers do not work, only native application is not a solution, only VM is not a solution, it's something that is able to encompass all of them, but also take care about the verticals that are used in the framework using different verticals, like in robotics, in cars, and so on and so on. But another challenge, which I think is also very, very challenging challenge, I would say, is about time awareness, because robotics application and automotive application, they have requirements on latency that may not be best effort. So if a car, for instance, is offloading its perception algorithm, the autonomous car, I mean, we could not say, maybe we receive the data in 1 millisecond, maybe like 90% of the case, but in one case we receive in 1 second, that's not good, because the car it relies on this information. So there is a need to be able to configure time-aware networks end-to-end, but the time awareness is not only on the network side, but also on the, let's say, virtualization side, because if you are deploying a container, a VM, a native application, whatever needs to be deployed, for instance, the case, say, take the case, this perception. This perception has to have also some real-time requirements on the amount of time needed to perform the computation. So this needs to be taken into account by virtualization solution like VIMs or hypervisor in order to actually schedule the application, to schedule the code to run at the right time. So this actually concludes my presentation. So thank you very much for your attention. I hope this was not boring. Now I'm open for all your questions.
Okay, thank you very much. It's a very nice presentation. Thank you. So let's go to the questions segment. Is there anybody any doctor in the room that wants to make a question?
Now we start the question. Thanks. Well, thank you very much for the presentation. Very interesting. Congratulations for the deep work. A lot of documentation, a lot of results, a lot of very complicated stuff that I'm not able to do. Maybe you know much better than me what is the challenge of all this implementation. Congratulations to your advisor, Antonio. So I have a few questions, curiosity, things that I didn't understand in full, or points which remain probably just touched in the thesis but not developed completely. So if we start with part one first, the first part of the thesis, which is chapter 2 in
Yes.
So you have this need of orchestrating in a way which is not the standard one, because you need to put together different components, different levels of orchestration together. You say, I can do this by altering a bit the way the real current networks in 3GPP work. So you have examples in which you have the now working as master or
Yes.
and then I have my proposal. So in the thesis, what I didn't understand fully is there any other option? I mean, is there only what is in the standard and what you are proposing? Nothing else that was proposed?
Well, there are other things, but they are coming more, let's say, they are being pushed down by cloud mostly. So we've seen a lot actually on, especially in that project, and in other project we have seen that, for instance, in ICOS. So in that case, that work was done in the context of GCD, so European project. In that case, we were pushing for that solution. But in the next project, we actually have seen that there are other solutions that are being pushed that they are like, okay, everything is managed by the cloud. So the approach is integrate everything on the cloud, extend the cloud, and don't bother about having an NFVPO that is actually an NFVPO. Of course, I think it's possible also to have other approaches, like approaches that maybe are more, let's say, more distributed or abstracted at a different level. But what I've seen, at least while working on the PhD and working on the European project, that first we come with this approach that was actually in that project, and then the other approach that came was like, okay, we don't care about the difference that there is between the cloud, the edge, and everything. Everything runs Kubernetes. Kubernetes can manage everything. Yeah.
I appreciate the fact that you actually distinguish the different tools that you have to manage to orchestrate and the performance in terms of memory, in terms of latency. What is not clear in there is, do you have any problem with consistency of data?
No, not in that case. But the testbed was I would say medium size because of the number of things that we virtualized, but we didn't have problem inconsistency. The problem inconsistency start to come when you have a more distributed deployment also on the testbed. Because ATCD, which is where the data is actually stored in Kubernetes, is kind of the eventual consistent storage with quorums. So actually what happens, for instance, in the cloud or when you have deployment of this Kubernetes in the edge for real is that you have replicas of ATCD. And this, usually, given that it's quorum-based, has a huge impact on performance. Because usually what you will do say, okay, I want to write information about the infrastructure with, let's say, I have 7 replicas with a quorum of 5. Because it can happen that replicas lag behind. This quorum of 5 means I have to be sure that I wrote on 5 nodes out of 7, which has a huge impact on latency. So by myself on the experience, I didn't experience any problem with, let's say, consistency. But the problem of consistency is always there when you need to deal with a distributed system. Because I think I also wrote in the thesis, when you have a real distributed system, there is the cap theorem that you cannot escape. So either you choose, so when you have a partition, either you choose between consistency, either you choose between availability. You cannot have both at the same time. So the way the cloud solves this is like, yeah, but we have like 5 9 availabilities. Yeah, fine, but when a partition happens, what is it going to do? We are going to be available, so have room for inconsistencies, and then being able to resolve this inconsistency when the system merges back. Or you decide, okay, fine, we are in a partition, we discover that we are in a partition, the system cannot progress.
Yes, there are a few words in this field which are about the atomicity of changes in the network and the way they are recorded and the consistency that comes from it. You don't cite those words which are more theoretic, I acknowledge that. But for instance, there are words of Antonio Fernandez in IDEA and also Nicolau, who is now in Cyprus, that built this Manipuri exactly on this topic. Definitely there's a trade-off, as you're saying, but there are techniques that manage to make the ledgers, for instance, lighter, and the way that you can parallelize and skip some problems that are typical of blockchain. By the way, you use blockchain.
Well, on that work, I didn't use it directly, so I collaborated in this case was with so Kili was working on the blockchain, I was working on the integration of the federation mechanism because it was based on the blockchain. But actually, through federation mechanism, one based on proof of stake, the other based on proof of work, and both then were integrated in the VIM. So my job that was integrate them in the VIM, and didn't use per se the blockchain.
Okay.
But my contribution on that work is mostly okay, we integrate this thing, is still the VIM going to work? Is still going to, let's say, behave correctly? Is still going to, let's say, taking the right time to deploy the thing, because this thing is going to explode and not working anymore.
Right. So there are some features in there which are typical in use blockchain or ledgers, which are typical of untrust scenarios.
Yes, which is very.
Also, what you're proposing to me is trustable. Is it or is it not?
So, actually, on the presentation just did, on the federation, I presented the part in which the infrastructure is trusted. But technically, I think with blockchain, depending on the proof, if you use proof of work, maybe you could also have a zero trust, let's say, federation. But it's not something that actually I developed a lot. Actually, it's not something that I developed.
That's why you can get all the way to the far edge, or because of even staying in the edge, you have the same problem. Right?
Even still, yeah, I mean, the problem at the end is the same. And it's just that you have different resources. Either you have resources like my phone, your phone, that maybe.
But that's a far edge, right?
Yes, that's correct. But in the case of the edge, you can, I mean, I'm not sure you really, I mean, on the edge there was an edge deployment. Most are tech operators. There is some, I mean, from factory we could claim the edge deployment, but that's inside the factory. It's not going out, so maybe it's not, they are not going to federate it anyway.
Well, I don't know. For instance, in the US, there is a AWS who's providing edge.
Yes, they do outposts.
Maybe there you might need it. Yeah.
But in that case, obviously the infrastructure is trusted because it's AWS. So when you call AWS as an AWS,
you trust it, but
yes,
but then forget about trustability.
Yes.
When you want to track, also.
Yes, of course. Of course.
I see the need in some
Yes.
cases of ledgers and all.
Yeah, because you get this kind of immutable reality of what happened on the infrastructure. So you can say, okay, I give you my access point for 3 hours, you need to pay for that. Because where it's written in the blockchain, and no one can change it unless you.
Yeah. Yeah, it's very interesting. Probably it's work for another thesis
Yes.
or two, definitely. Can you go to slide 11? About this heat maps that you showed. 11 and 12. There were heat maps about RAM, load factor, and this one.
This one, for instance.
Why are so irregular? I mean, I was expecting a thing like the second one, the one in the middle.
Mm-hmm.
You increase the number of containers per node, you increase the number of nodes, and things get worse. Fine. That's expected things. On the right, you explain there are some mechanisms in the cube edge that make this inefficient, let's say, for some. But what about the left part? I mean, why you have some green entering in the middle, then blue taking control of the
So that I think is a mix of, say, Kubernetes, all the service needs to communicate. So but they are not like in the case of Kubernetes, all in the same nodes. So the network latency, although they're on the same node, still pays so still has an effect. But also there, I guess, mostly comes also, etcd is in everything, and it can happen, but it's going very low level that you're fetching that information is in cache, so it's faster. I don't need to go fetch it on the RAM. But most of it, at least when measuring the thing, was that the actual services need to communicate between themselves, and there could be a service that is slower to respond to the other in one case and faster in the other case, and this is why, for instance, we have like this happening or this happening.
Yeah, I'm more concerned with the part in the middle where blue and
yes,
green.
when blue and green mix. Then blue and green there, I mean, it's like bluish, greenish kind of, so should be around there. So there is not that much impact.
What's the unit in there?
So there, this is the deployment factor. So like this, so it's like this divided by this.
So what we are talking about, maybe going from 30 to 50.
Yes, maybe it's going to 30 to 50, which is a lot, I would say. Which is a lot, but I mean, it's a distributed system at the end. So as nodes need to communicate, there is some latency. One microservice could be doing the job, could be doing a job, so the job gets queued, it takes more time. While in the case of KubeEdge, everything was pushing the same binary, so there is actually all this overhead is not there, and actually you can tap directly when you need the information.
And this is the average, by the way, because then
Yes,
probably
yes.
it's much more
Yeah,
distribution that should be.
Yes,
should be-
I don't remember how many gigabytes. I think I have more than 2 gigabytes of data for this thing. And actually was fun because in the paper, and maybe you've seen scrolling the thesis, the PDF of this picture is so big that it pops up, like, it pop up like an animation. I don't know why. why this thing pops this way? It's because the PDF is too big, too many data.
Yes.
I think it's not that. I think the other is the 50% like, if I'm not
The
wrong.
median.
It's the median, I think.
Okay.
But
Same problem. I mean,
Yes.
it's one point of the distribution
yes.
and then the other. For what concerns the next one, the
RAM?
Yeah, RAM. It's not about. What we were saying before is the same here. My question is going to be about the load factor. So you define. Can you repeat the definition of load
So
factor?
is the one between the slide, is the RAM used when you have actually 0 containers running and 10 nodes connected to the master? The other way around. The amount of memory used when you have X the containers per node running and Y nodes connected to the infrastructure divided by when you have 0 containers running and 10 nodes. So it's like, let's imagine this divided by this.
And this is taken where?
As far as I recall, was taking the one that was using less memories, which is KFS. So everything is normalized on the one that takes less memory and the same taking less time for deployment.
But when you go for the case with the 010, let's say 010, don't you have also use of memory in remote machines to provide?
So the remote, yes, but I didn't want to measure the amount of memory they require on the compute nodes. So this memory used on the controller node. Only the controller, yes.
But what I mean is that there are some functions that probably you need to centralize in a case and decentralize in the other case. So the total amount of resources used
Yes, will be
not
different.
only there, it's also in the other.
Yes, of course. But I did some monitoring on the compute nodes. The amount of memory and CPU used on the compute nodes, or in general, is related to how many containers are running there. So if the compute nodes are actually doing nothing, yes, there is some RAM usage, but it's very low compared to the controller nodes. Didn't want actually to do this evaluation on this work, but of course it's something that can be extended, and they say, okay, this is the impact on the controller node, but this is actually the impact on the compute nodes, because they are not, deployment doesn't come from free. So also there will be an impact.
Well, also the fact that you run multiple containers on the same machine may have
Yes, it
some
doesn't.
linear bypass and the use of RAM and the other.
Exactly. Actually, what we have seen is that there is when the scheduler deploys the thing, it doesn't deploy them all at the same time, except for KubeEdge because implementation is bad apparently. It plays them. And we have seen that there are spikes on memory utilization when it's time to actually create the container per se. When the container is running, the memory utilization per container is quite stable. So if you have like 10 containers, you have almost 10 times more than when you have one container. But the impact on there also depends a lot on the workload. So in this case was an Nginx server that was deployed that doing nothing uses around 20 to 30 megabytes of RAM. In that case, we'll maybe sense, okay, let's imagine you have this application, I don't know, it's an MEC platform that gets this amount of requests per second, and see how many MEC platform, how many servers that get this amount of requests per second, we can deploy in those compute nodes. Because there we have an actually workload running for years, not just sitting there waiting for a request.
I don't want to take too much time, but I have another question about the part 2. It's a fundamental, maybe something I don't understand. So you start, both in the presentation and in the thesis, with saying that this is all is about data flow programming. It has to do with MLOps.
In that case, yes.
Yeah, at least in that case. So there are two things that I understand. One is if what you present is specific of MLOps and to which extent. Second is why in the result I don't see anything related to MLOps.
Okay. So it's not per se the framework is not related. Is not, let's say, tied to MLOps. That was one use case that was coming in this case was from Demon, from a collaboration with another university. And we decided to evaluate there. So the framework per se is not, let's say, tied to MLOps. On the thesis, I didn't want, so there is actually one graph that I didn't want to show you. It's kind of strange to explain, which is there are no sort of MLOps because I was not focusing on the MLOps part per se, so like on the time needed to training or on the accuracy of the training, because usually it doesn't matter how you deploy the model or how you deploy the training, that should not have an impact on the training result. If there is an impact on the training result, it means either you're doing something bad within the training or you are impacting the data that is being sent to the training per se. So actually there is one graph in the thesis that shows the accuracy over time.
Yeah, okay, I remember the accuracy. But then all the rest is not really related to
it's not related.
So I wanted to understand if all the procedure, the way that you are structuring, designing the solution, and opting for the data centric has a strong impact on the MLOps, at least not to say any machine learning approach that needs to use the perception.
Yes, so the impact is mostly on, let's say, all the developers are going to write the MLOps per se, and all they are going to deploy them. There is little impact on the actual, let's say, training part, on the actually machine learning part per se. It's more on the operational side rather than on the let's say, training side. But yeah, I agree that that part will be maybe written more clearly.
No, but there are many things. I also understand that the space is limited, the time that we do the presentation, but I added out at some point if I missed something.
So I can tell you, when I started writing the framework, machine learning was not even in the, let's say, was not something we were thinking of.
That's my impression. That you
Yes, exactly. So when we started writing the framework, was about, okay, we want to simplify developers building things. In that case, was robotics developer, autonomous vehicles developer, and then we said, okay, but maybe we could use, so we had actually in Devon, in which we have MLOps, we have deployment for MLOps, but can maybe this be useful there? Can we see if we could achieve like cloud to think MLOps, or can simplify writing of this MLOps pipeline? So that's why we took that, we did that work.
Okay, another curiosity about slide 38. You have two cases in there of service discovery and non-service discovery performance. One has high variability, the other has very low variability. Why? Because service discovery per se has a strong impact
Yes.
and is almost constant in time.
But yes, those are the results. Yes. So what was up in the service discovery has to do a lookup somewhere to know where the services are. This lookup has a huge impact on the thing, so that is core shaping, because most of the time this case was a lookup on a national, which per se has no variation, because it's not in the same process very quickly. But doing this one more call was squashing all the variation, because most of the time was spent there to the calls doing the service discovery. And actually, was in this case, there were so total are 5 calls, and so the call of service discovery are this one and this one. So this one had very low variation, and because they take all them that time, and they were squashing all of them, all the other at the end. And I don't remember how many samples we had, but I think it was around 100 to 200, even more. I don't remember.
Okay.
But as you can see,
more
for
questions, but I think we should stop and pass the words to other committee members, because otherwise we'll not finish. Thanks. We will have time to discuss more later.
Okay.
Thank you, Ignacio. So, Gabriele, first of all, I would like to congratulate you for the work, and also I extend these congratulations to your advisor, Antonio. Also, I would like to thank both of you for having me in the committee. It's a pleasure to be here, as always. And I'm not Italian, as you know, but I would like to say just congratulazioni, which I think is more or less the thing that you say in Italian, for congratulations, also for all your family that you have had the effort to come here from Sicily, which is something to be highlighted. I was, so the PhD is impressive in the sense that there are quite a few things that make it, let's say, singular. First of all, it's a fully implementation-based thesis. I guess that most of us know that this is sometimes not very well rewarded by the scientific community. You just put a lot of time into fixing the things and just to get one line less of code. And I understand that from many people this is just meaningless because they don't read the
Yes.
So the return of this type of work sometimes is not well acknowledged, and I do believe that it's very, very important that there are also theses working towards having real implementations that are not only you have been discussed here and you have presented it here both in the thesis and in the presentation, but also it's something that is part of what you are doing in your company now. So I guess that when it comes to contributions, what else can you contribute? You are making something that is already there in the
Most of the time, yes.
So I think that is something to be congratulated and to be proud of. So thank you for that. The presentation has been very good. The thesis is very well written. I like it a lot. There are some figures that probably you should have made the effort of having a more homogeneous way, because some of the figures have a very large font, which actually, but it was very well written. It was very, very easy going through the document. So I like it a lot. And as Vincenzo, I have also some curiosities and questions that. So you have already answered one of my first comments to the first part, which is whether your contribution was on that part. Because I also had, I don't know whether it was lucky for you or not, but I was also in the committee of Kirill. Okay. So some of the things that I have seen today, I saw it also in Kirill's PhD. So yes, I wanted also to ask you about the different contributions from your side and Kirill, but you have already answered that. So can you, something that, I know that in time probably that was previous to the work that you have been doing in Sena, right? So that work was done before.
Okay.
That's a question.
So the work that was done, I was working most of it on both, let's say, at the same time. But the work on the first part, which is the work that actually I did when contributing things to Eclipse for OS, was done before the work I did on the second part.
Okay.
That is true.
Yeah, because this question is because in the robotica scenario with the virtual AP, you are using MQGT. Yes. The question is, would it be possible to use Steno?
Yeah, of course. It's just that we use MQGT because in that case so I didn't wrote, for instance, the algorithm. One contribution was the integration of the algorithm there, and this is the decentralized virtual infrastructure manager, or porting it worked there, and the algorithm was already using data coming from MQTT. So we didn't bother porting it. The algorithm was there.
But it would be possible.
It would be possible, yes.
And do you think that you get some benefits? If
You will, for sure, we get lower latency. That's for sure, because the way Zen is implemented, the way serialization is done, and so on and so on. And I would argue that if you use Zeno, maybe you could also extract this kind of context information in an automatic way also to cloud application. Because you can have, let's say, Zeno per se works in a routed manner. I think it's written on the appendix of the slide, on the thesis there is the paper about Zeno that explains how actually it works. And Zeno can work in a routed fashion, which means I don't need to have only one broker, but I can have an infrastructure of routers running everywhere. Which means that we could have like a Zeno broker or router running on the MEC servers, but we could have one running on the cloud. And then maybe I could have an application connected to the one on the cloud that could be able to receive the radio network information from the edge in a way that is completely transparent without needing this application to connect to the device, to the edge. You could just connect to a Zeno router on the cloud, you get the data.
Okay. Also in this part, I have two more complete questions and then I have a more generic one. So let's start with the complete one. When you are working about the DLDs and the blockchain, you have also answered a question from Vincenzo in that particular part. But I was wondering, in the slide 21, if you see the times are they are seconds.
Yes,
there is seconds.
Yes.
So this does kind of. I mean, if you are trying to use this in a real-time environment, I don't know whether this is thought to be used in real-time decisions, or is it something that you do offline, or you do once and then you just start using it because otherwise it doesn't fit, right? So
yes. So the point there was actually we can see that the federation per se part, so the part that is about either blockchain, well, either proof of work, proof of stake, it takes longer time. Which, if we look for instance the previous slide, in this case this one, means that maybe we need to change the thresholds when we need to deploy the service, to deploy it, taking into account that it will take more time to deploy the service compared to the case where there is no federation. So it has an impact, of course, but this impact will be kind of, let's say, alleviated by having an algorithm that is smarter when deploying the things. Let's imagine the case, the robot is delivering a good from this university to the center of Madrid. We already know the path that is going to follow. We already know the exactly waypoints. So in this case, although the federation is taking more time, what we could do is okay, fine. We know the waypoints, so we know that at that point on, it will be outside of our coverage. So we could prepare, we could do the federation procedure before and instantiate at the right, let's say, bit before compared to the
okay, wasn't that what they did with this emergency use case that they use in Kirill's PhD program?
I think so.
Okay, yeah, makes sense. I have just a curiosity here. In this figure, what are you writing in the y-axis? What is period? Is it probability function?
Yes, probably.
But it can be, right? Because you have the distance there.
Yes. So as far as I recall, that was a probability function of. Yes, you're right.
So that is just probability.
That should be the
probability.
so
Yes.
well it should be probability. Exactly. So I think it's there is miswritten there.
Okay, so it's not that.
No. That's the point. Is the point probability at that distance of the figure. Yes.
Okay.
Ah,
And then if you go to slide number 16, please.
16. Yes.
Here I was, I'm not, I mean, this goes beyond what I'm used to, but I was I have some questions about the way that you are using this maximum CPU load. So, how do you measure this? Is it just something that it goes just a nanosecond and then you put it there, or is it something that you have to have for more than?
So it was data coming from the monitoring of the infrastructure, so from well-known monitoring system like Prometheus and Grafana.
Okay.
And in this case, it does kind of an average, I think, on 5 seconds because it's the load factor. Yes, so
Okay, so it's something that you average for a time window.
Yes,
right?
it's not
okay.
So I mean, it will not be like 36%, maybe spikes to 80,
Oh,
but
okay,
then
okay.
in that 5 seconds it takes that.
Okay, now it's clear. Okay, so very interesting in this first part. I have just a kind of more conceptual, fundamental, philosophical question.
Okay.
What is the difference between fog computing and edge computing? Because you wrote in the thesis that there are clear differences. You have put a figure in the presentation, but then when you start working on things, you just talk about edge. I mean, fog is mentioned, but it's not really, used, or at least I didn't see it. And so I just need to, because I myself I don't really understand the difference. Sometimes I wrote edge, sometimes I wrote fog, and I don't know exactly. So if you, this is just a philosophical question.
Well, it's a question that a lot of people have, because first, so when you think about edge, what is the edge? Because if we talk with guys like talk telco guys, say the edge is where the radio access network starts. But if we talk like with people with, let's say, someone in the industry, say no, the edge is the service that I have in the factory. So the telco is it's another edge. There is already distinct what is the edge. So like when we were working, like in this case it was in Eclipse Edge Network, it was like, okay, bring your own edge, we don't care. So the edge is where you want to be. Fog is kind of, let's say, philosophical, because there are people, especially like from IEEE, was 1934 was the old Open Fog Consortium, that fog is actually the cloud to thing continuum. So it's all the device from the things up to the cloud. Someone calls fog only the far edge part, so only where we have like my phone, your car, and so on and so on. So actually there is, I think at the beginning of the thesis, I take that definition of fog. So everything that is below the edge. So everything that is not radio access network, everything that is not like on-premises computing, something that is not well connected, that relies mostly on like battery or is mobile. That's what I took as a fog definition. Then for the thesis, I was mixing edge and fog because, again, is the robot real fog or is an edge? Like the robot the room that is running at my place, it can be used as an edge device, can be used only as a fog device, because maybe I can offload some of the street because it's not going to go outside of the house.
So there is not a clear.
No. There are a lot of discussion, but once the time there was miscomputing, and now it's.
Okay. So basically, I can understand that. So for, I guess that also there is a large or kind of a big avenue of research there, because when it comes to the real fog, if it's all our devices, I mean, trying to handle the distributed, if you are just distributing the services, the computing, that you have to move from one device to another, that of course is a huge problem that you have to tackle.
Yes.
And do you think that your proposed technique could help to deal with this extremely distributed approach?
So I think there are a few things that could be taken, could be used, like maybe having, for instance, when I was doing when we was working like on Eclipse Fog 5, was like, okay, we don't want a centralized thing because things might disconnect. We don't want a constant stream of data for monitoring. We want something that is able to fetch data when it's needed. That, for instance, thing would be taken and be used. Let's imagine we want to orchestrate all this architecture, And we maybe don't want a centralized orchestrator. We want, like, I don't know, election algorithm to decide each time we need to deploy a service who is the one that is going to take care of instructing the others, but also about monitoring. I don't want to get cost information from my phone, let's say sending from my phone to my home router because the status of the phone, because we're going to drain the battery. Just as simple as this, even if they are connected. So maybe only in the case when something is needed, you can fetch that information and use it as fresh information without needing always to pull the data. But this also has in general impact on all the orchestration algorithm, because nowadays orchestration algorithm takes that the infrastructure is there, is not going to move. If a node disappears, is a problem because maybe the disk broke and we need to move things immediately to the other node. But let's take the case of a car. I want to deploy a service, for example, inside the car, an infotainment service, maybe some streaming the service server inside the car, but then the car disconnects. Do I need to deploy this service on another car? Maybe not, because it's still running on the car, so the car may be still able to work, and maybe I just lose connectivity on the control plane, but not on the data plane. So maybe the user is still seeing the video, but I cannot reach the information on that car. So yeah, there are a few things that could be taken, a few things maybe could be done in a better way. I think it's a good starting point.
Okay. Okay. Let's move now to part 2. I will try also to be short now, so not to take too much time. You haven't put this figure that you have in your thesis when you compare the throughput between Zeno and things over TCP.
I have it in the backup slides.
My question there is that at the end of the day, Zeno is also using TCP, right?
In that case, yes.
Okay. So basically, what you do in Zeno is to put some. How does it work in the sense that you put
this one, right?
Yeah, that work. So here, if you are using TCP, why do you have the improvements?
Is the way Erdos work, the architecture of Erdos work.
So it's kind of
it's mostly say implementation detail.
Okay.
Per se, because Zeno is able to do fragmentation of the data being sent. He is able to do. He has a better acceleration format compared to the one that was used by Erdos. And also the way Zeno deals with TCP buffer is a lot of
it's a lot of coding.
It's a lot of implementation. Yes, it's a lot of implementation to be sure that performance of Zeno are good enough to not impact the perspective. Because this one are actually plugging Zeno directly underneath Erdos. Because I think I also slide here the performance only of Zeno that are always also way better. So still, the architecture of Erdos has an impact on the performance of Zeno either way. But when using directly TCP, it was, as you can see, it was not well implemented.
No, it's pretty impressive. Not only the improvement you have in the throughput, but also the variability. It's
yes.
Kind of
overwhelming.
overwhelming.
So I remember when taking this result, of course, I was always monitoring the process, so like CPU and buffer utilization. I would see that actually what was happening in Erdos is that it was not filling it was sending too much data without waiting for the data flow to come, like ACKs and this kind of stuff. So if you were filling, so then all data was going out, then no data was going out because TCP buffer was full, and so this is why.
How do you? I mean, this is just a very concrete implementation question. But who do you, from the scene architecture, how do you get aware of how is the situation there, so you can change the pacing?
There is a queue before.
There is a queue before. Okay, so
There is
a queue before. Okay, that's interesting because we have been doing something with Quick protocol, and we have implemented, and in Quick you have this multi-stream feature.
Yes.
And if you are using the regular Quick implementations, you just don't really get too much benefit from this multi-scheduling between this multi-stream thing, because actually you cannot queue the data.
Yes.
So what we did was to put another queue
On top.
between the application and the Quick protocol, and that was all. I mean, that was impressive that you could do a lot of things, because actually you could,
Or you can schedule.
Yeah.
So you can get
So
for
you
instance-
did something similar here,
Yes.
right?
So because for instance, let's say we want to try to send on TCP buffer. The TCP buffer, I cannot send. I will block. So okay, maybe I will like back off. I don't know, 10 milliseconds. Maybe those 10 milliseconds are enough. But as in also this slide, we can see that the fact of Zeno being on top of TCP has of course an impact on the latency, because latency of TCP is better compared to the case of Zeno. So of course it is related on TCP in this case.
Okay, just this is my last question. Yes, can you go to slide number 31, I think? It was 31. So here, this bursting, it's not 1 millisecond, it's 100 milliseconds, right? Or do I miss anything? Because
Yes, it's 100 milliseconds, yes. I
Okay.
misbrought, yes.
here I was completely impressed by the good results of Xeno. 50 microseconds is nothing. So I was wondering how is the platform that did the results, because
So everything was running on the same machine.
okay, so it's just computing,
It's
pure computing.
Yes, your computers have the look back
Okay,
pointers walking
then I
there.
understand, because then I was not able to see, okay, if you are putting some network in the middle.
Well, we have the result of Xeno with network in the middle, which is, I think, are on the backup slides. So we have a test bed, which is with 100 gigabit fiber.
Yeah, that was at the beginning of the thesis, right?
I think it's on the appendix.
Okay.
Because in the appendix about Xeno performance and so on. And there, I think we reach very low latency, because it's very low latency I2 network in that case. And TCP is configured in order to achieve this kind of stuff. In this case, was running on
And also the MQTT was the same, was in the same machine.
yeah, for same machine, exactly. But as I said, the problem with it is that, especially so, let's say in this case, the pipeline starts is fine. I'm going to receive data from all of them, and I need to send it downstream. Fine, but as the pipeline starts to fill, I will have more data going through the broker.
Okay.
And which is the broker has to actually route those data. And routing those data, of course, has a cost on the latency. And that's why if all the data comes to one, the cost will be higher. If just few data comes to one, the cost will be lower. That's why we get this kind of step distribution. It's like that we can see a different state of the system, actually.
And now, as I did in the first part, I will finish with a more conceptual philosophical
Okay.
question. You've mentioned in the thesis a couple of times 5G, and in fact you did one of the use cases was kind of touching 5G and beyond 5G networks. And you have mentioned also NFV. I didn't see any mentioning to, which is kind of the de facto standard now for NFV, which is Open RAN, and these new approaches to deal with the division between the RU, the VU, and the CU. Maybe this is a little bit out of topic for you, because that's where I'm more, but my question is, in that part, I see that the interest in the architecture, you would see like you need to have a lot of computing power to do what you require to take all these functions that they come from the remote units and the antenna to the edge, to the cloud, wherever you want to put it. And then I assume that if you are dealing with this, how the networking and the computing realms are going to be together, you have to somehow, the work is even more challenging, because you have to divide the computing power between the two things, right? So there's something that I would like to comment on that. And the second question is, one of the things that, and also your advisor is very, I know a lot about this, is the ISAC, and I was wondering whether all the things that you have been doing could be somehow also used for this integrated sensing and communication, or gathering all the information, because Seno is very, very, very quick. So
yes, so you could actually you could use Xeno to gather the information. Like said, that should not be an issue. The only thing is verify that, let's say, the performance of Xeno are good enough to keep for the pace of the information to send. Because it can happen that, okay, say I have a deadline of 3 seconds, fine, and you can use even against distance, not a problem. I have a deadline of maybe 10 milliseconds, okay, then maybe using Xeno you can achieve it, maybe not, but also that depends a lot on the deployment.
okay. And regarding the way that you can share computing power between
That I think is also, it has an impact on the way you schedule the things on the edge, cloud, or whatever you want to do, because there are, in this case, the RLU is kind of, I would say, a real-time system, because you have to do some computation that needs to be done, or to, let's say, calculate the amount of power and signal you need to send on the antenna. And sharing those resources with, let's say, OTT resources like developer application is indeed challenging. But that's maybe where also the time awareness enters, because say that deployment is time aware. So that deployment now I need to schedule like the first 10 milliseconds of this second for the CPU, because he has to do the job. He cannot be delayed. The REST API of Facebook, who cares? It's not time aware. I mean, what if because the interaction time is very different. One is machine time interaction, the other one is human time. So yeah, we know that if the page takes 1 second to load, we are upset, but we are upset. We are not destroying like all the
you mentioned that in the thesis, and I completely agree with that. Thanks a lot for
Thank
your
you.
question, Carl. It was very interesting discussion. Maybe we can take it also
Yes.
sometimes afterwards. Okay, thank you.
Thank you very much. So let me start among that is not so appreciated by other people, but I think it's very important. It's just the reason to have industrial PhD, and I think is in that way you have made a very good work. I really appreciate all the effort that is put in the thesis. I think it's a lot of work and really is really interesting. For me, it's very sometimes very difficult to understand all the things that you have written here. That's me. So congratulations also to your PhD episode. I have some random questions. Mostly are details, not very philosophical questions, as most of the philosophical questions have been already asked. So just please to the slide 12. This question has been already done, I think, by Vincenzo, but I have two curiosities here, because they are not really questions, but are curiosities. First, Vincenzo mentioned this, but I didn't really understood. I didn't really understand the point. So you have for example, in QH, you have the row for 50 nodes and the row for 60 nodes.
Mm-hmm.
And the RAM row of this was with 50 nodes with 60. We have some node in 40, we have some node in 50, and we have some node in 60, and it's going down and up.
Yeah, so that's, I think, is also to do with how many things are going to keep in cache by the etcd. So this is, again, it's most implementation detail, I would say. But there, the problem, so I said, there is the etcd thing that is an in-memory storage. So what it will happen, he actually is in memory, but he also is able to upload things to the disk when it's time to. So there, for instance, most probably what was happening is that, yeah, there is, again, is between, let's say, 3 and 4.5. Maybe, so there was a bit more RAM that was used. So in this case, for example, 60 was more than 70 in this case, because this is like also like an outlier for this or like that. But this was happening because of actually the implementation detail of Kubernetes works. So it can happen that a few things are actually kept in memory, or that a microservice is using more memory compared to the other because it's fetching more information at that time compared to the other, and this of course shows an impact on the RAM.
Kubernetes, is different with different number of containers and so on, but in Kubernetes,
yes,
you have.
Well, Kubernetes is
stable.
Yeah, but Kubernetes is because if you keep in mind in the architecture of Kubernetes, if I manage to do this, my phone, my PC managed to put the slide, is always connected to Kubernetes API server. So it keeps some information about the infrastructure, but it only gives way less information compared to Kubernetes. And it also takes some information about the things that deploy on this infrastructure. So if we take, for instance, a look at the RAM utilization, the Kubernetes server where this thing is connected, we have actually the same behavior as in that one. So we will see the computer once. So if you take so this is stable, still goes up to 2 times, but it's stable. But this is connected always to something like this. So if you take a look at the RAM utilization of this connected to this, it will actually be like this, like the same. So that's why there is actually no impact. And it's mostly because of the architecture, the way the Kubernetes architecture is done. But again, for example, there were weird things happening, but that's the result. That in the case of 50 nodes, we're actually using less RAM than 40 nodes there. And there, my informed guess, looking at the when the things were running, looking at what's happening, is that it was just freeing some memory. That was happening, and understand exactly why we actually look at the code of Kubernetes. Okay, maybe the garbage collector for kicking and create memory.
So another point in this figure is that you mentioned that the cost of nodes is higher than the cost of containers.
Well, we can see like this.
Yeah, but the containers go from 0 to 10, and the nodes go from 10 to 100. So
yes,
the comparison is a little unfair.
Yeah, but these are nodes. Yes, it's unfair, but those are nodes per. Those are containers per node. So actually, those, for instance, in this case, there are 100 containers running.
Ah, okay. So yeah, I missed that. Yeah.
So this means that 100 containers in 10 nodes take less than 20 nodes without containers. That's why we, as I said, is dominated by the information internet infrastructure. But as mentioned by Vincenzo before, if we take a look at the compute nodes, in this case, the compute nodes will have more RAM used. Why so? Because of course there are more containers running there. But in the case of the master, the information needed, say, stored is dominated by the amount of information on the for the infrastructure.
I understand. Yeah. So check. Yeah, this was mentioned also in research, I think. Okay, so it's related with the use of the ledger.
Mm-hmm.
You mentioned that it's not really your topic, so so it gives a lot of time, so a lot of delay.
Yes.
Everything 19 seconds seems too much, even to think that I am going to deploy the service earlier, so 19 seems too much. I'm not so sure, because proof of work seems that it's not really going to work because the delay.
Yes. Right. I think in the slide there was proof of stake.
Yeah, and proof of authority.
Proof of authority, yes.
You mentioned. Yeah, but if you have proof of authority, you have.
You don't need a ledger.
You don't
Yes.
need a ledger.
You can use some of the database. Yes.
That's my point. Yeah.
Yes.
So I don't know if you have any further comment on this.
So I remember when doing this work, I remember in this case that because that part of it did by Kirill, and when integrating we were discussing, it was presenting with those different scenarios, and actually was, I think, proof of authority you get, still you need some time to federate because we need to communicate between the infrastructure per se, but proof of authority has, you could have better result than proof of work, but with proof of authority, you need to trust the authority. Well, with proof of work, maybe you could do a zero trust. It's always, as in engineering, is always a matter of trade-off. Can you afford having more time but being able to deploy on whatever infrastructure with zero trust, or you need something that has very low delay but you trust the infrastructure? It's always a matter of trade-off. It really depends on the use case.
Slide 73, so it's really one of the additional slides, but you already showed it to the programming things, so I don't want to take the opportunity to take additional.
This one.
Okay, so I think this somehow like strange to me the fact that you have some message per second and then you go to zero and then you go up again.
It's not actually zero, it's very low. So because there is still, it was around 10 to 12, and there was, so this is, again, it's not plain TCP, it's TCP used by FDOS. There, I think we were closer to the fragmentation thing of, to the computation of the fragmentation of TCP, if I'm not wrong, but it was not actually going to zero. So we had the similar behavior with the MQTT. TCP actually performs stable up to a certain amount. Depends of course on the configuration, on the buffer size and so on. So it performs stable up to a certain amount, let's say, of payload. Then fragmentation kicks in, and so you get very low throughput, I would say, and then it kind of go up again and then go down. That's, I think, depends a lot on the implementation of TCP, because it should not happen.
What do you mean with fragmentation?
I think this was a P before, so it was happening at IP level.
Yeah, but I mean, if you have TCP should.
Yeah, but depends how things are configured.
Okay.
I think that there was, sorry, it's not really fragmentation, what I think, as far as I remember, looking at the process running, was about the buffer size and so the buffer size on the TCP side and the buffer size on the application side. Because there, the applications, so the buffer on the application side is kind of unlimited, while on the TCP side, of course, has a configuration that was the default one, and this, of course, has an impact because we try to send, I just sent 10 bytes, I can send the other, I send, in this case, it's many 10 32 kilobytes. He will tell you, yeah, I send the first 16, but then the other 16 you need to do the backoff to send them. So does it actually has an impact, of course, on the message per second you can send, because your message is 32, is not 60. So you need to send it like at the pace of sending 2 messages, you just send 1 message. And this, of course, has an impact on the thing. Then that's really, I think, depends on the way TCP and the window are configured on the machine. It goes up again and then starts slowly go down again. Yeah, I remember when looking at it, I was like, okay, look at the process and look at the size of the window, like window being like empty. It's like, I mean, empty in the sense, full. So no more things will be sent, empty, full, empty, and then we'll get into the results.
When you see a graph that goes up and down,
it's always strange. But I mean, we repeated the test multiple times. We were always getting the same data. So that's what is happening.
Okay. So the slide with the overheads of the different not the throughput, but the different overheads of Xeno compared with
This one?
yeah, this one. So again, it's a curiosity of a minor detail in reality, but how do you find overhead there?
So was the amount of data, the amount of data being sent over the TCP socket in this case, removing the actual payload. So we are measuring actually what is the overhead of the Xeno headers or the other headers.
Okay, so headers and are down to the
TCP. Because all the solutions that are based on TCP, so
Okay.
TCP as our transport, and then we took, okay, if you are sending, for instance, 100 bit as application on TCP, with Xeno we send 109. So the header of Xeno is like 9 bytes. So that's what we define as overhead.
So can you go to slide 26?
Yes.
Yeah, again, this just to understand. So here, you mentioned that Xeno deploys the applications across the continuum. So across means the intelligence to do that is in the network definition, the network service definition, or
So the framework per se, so it works on an agent-based way. So you have different agents running on the infrastructure, of course, and then the developers can give some means when it's time to deploy. So like these components needs CUDA, so it needs, of course, an NVIDIA GPU. This one needs access maybe to an actuator because it has to move the motor and so on and so on. So the idea there is to take part of this information and send it to the Xeno flow, and that's the magic, send it to the different nodes and verify the one that are say compatible with this annotation. If there is no annotation, you can run everywhere. If there are few annotations, is to take care of them in order to do the deployment. The annotation way was not only let's say one that we investigated. We also took actually implemented one that was based on tags. So like you can give tags to compute nodes, and then you can have the same tags on your application definition, and then you try to do the match between them. It was very complex to do with say access to hardware. Like I need an microcontroller. I need an actuator there because needing this actuator because maybe it's connected through serial means I'm going to be exposed them to the application. That was kind of painful to manage something. So we managed the POC, they managed actually to implement it on the product, and we managed to do some work testing it, say to validate it actually.
so the reason for including more intelligence to, for example,
We will say yes.
because you are dealing with edge and cloud, at least to decide that it's okay, not within the edge, but knowing that the component must be deployed in the edge.
I think there is a lot of room to add more intelligence in it's mostly on the scheduler per se, because the scheduler nowadays is quite simple, takes a look at annotation and tags, and does the trust with the match. But for example, this doesn't ensure that, let's imagine you have one of these components, you want to run it on the cloud. You should not be aware of, but you say, I want to run it on the cloud because I have an agreement with AWS that if I use those amount of resources, I spend less money. So maybe there more intelligent, of course, could be added to in order to kind of simplify all this deployment or make it even more smart. Because nowadays, yeah, it works, but it's quite simple per se.
So, slides 16. I can do a lot of random questions and the random words.
No problem.
So, yeah, I mean, clarification that so all the inputs for the different, let's say, orchestrations, possibilities are the same.
Yes, it was
You are only changing
the way they are arranged.
where they are.
Yes. So actually, the service request there was a service composed of 2 VNFs and an MEC app. So it was this MEC app needed the 2 VNFs. The MEC app was providing a communication platform. So actually was using Xenos MEC transport in this case. That was the service exposed by the MEC app, and the VNF were 2 VNFs. And the service deployment is the same for all these scenarios.
So it makes sense to me the results, so it makes all the sense to have a centralized orchestration that's independent of the different components. But I have a question related with the fact that you are using three nodes in one case and 2 nodes in the second case, so the comparison of CPU.
Yes, but because that's where we wanted to focus with this work was the CPU usage where we have the orchestrator doing the actual work. Because the MTO per se, it does have an abstraction, but it doesn't need to deploy things. So it doesn't need actually to check if the VM is running, it doesn't need to check if the content is there, it doesn't need to do the actual networking, the actual configuration of the network. So its work per se is not that complex. It's most of the time, okay, deploy this, okay, I will check if, tell me when you finish the deployment. So we have one more node, but this node first it can run almost say everywhere. So you can decide to run it at the edge, you can decide to run it on the cloud, you can decide to run at the fog level, as we said before. But yes, you have one more node. So, but the point there is that the nodes where you run the actual orchestrator, the CPU time is way more important than the CPU time when you run the MTO. So that especially this is true, especially when you see the case where the edge orchestrator was a master, because in this scenario, the edge orchestrator was running as edge thing, so was an edge resource, so was one virtual CPU and like a few gigabytes of RAM. So that the cost of that CPU, so the amount of work done by that CPU is important to deploy MEC app, not to deploy NFV app. So why we should use it to deploy NFV app? That for that we use the time for the NFV orchestrator, but then the NFV orchestrator is to deploy VNF. Doesn't need to deploy MEC app, so it's kind of recursion to say, okay, let's try this solution. Of course, we have one more node, but that node actually has could be deployed first almost everywhere, as long as it's able to reach the other orchestrator, and it doesn't need to do way more work. It doesn't need to do actual work. It doesn't need to kind of passing papers to the different orchestrators to be sure that the infrastructure is there.
So, two more questions. So, slide 30.
30? Yep.
So, I'm not sure if I am interpreting this correctly, but so in the MQTT, it seems that the training is done in sequence.
Well, it seems that it's not done in sequence, it's done in parallel also.
Okay, so it's just,
And maybe that should have been figured is better, but I said.
Just wanted to be better. So, last question. So, slide 34. Yeah, so there is, it's a little bit, not very philosophical, but a little bit more. Yes, that's so you are proposing to use your system to implement the 5G architecture or
Yes.
the beyond 5G architecture. So to do that, you mentioned that you need that the network functions are defined as microservices.
Yes.
So the question is, how difficult is to do that with the real functions of the 5G?
There is a lot of discussion happening in 6G project about how to simplify those functions, because current functions are actually huge. There is a service base, not a microservice-based architecture. which is easier to define, but then you end up with like services having 20 API calls and needing a state, but then the state could be centralized, and so there is actually quite work that being done in the CCG standardization in order to simplify those functions and to actually decompose the current services into microservices. Per se, I was when looking at the document to actually work on this, when looking at the standardization, see that few things that we say are easy to decompose, like some few services that are easy to decompose, like I don't know, I think the MMF actually had a few calls, but they were easy to decompose. But other services are way more difficult to decompose because they kind of an internal state or they state cannot be really externalized because it will have an impact on performance. So is something that has to be done with a grain of salt. Okay, maybe few services could be like really simplified and made stateless and serverless, while all other are going to remain service. But this is kind of an iterative process. So you can start by decomposing one service and still use the other ones as normal service, and that will happen in different releases. I mean, it doesn't need to happen like at once. You just can do that in a iterative way.
Okay, so CDP is really working.
There is work on the is on 6G projects actually on flagship project about this, about trying to understand all those things could be simplified.
It's identity or is
well, but then those projects try to push to 3GPP to. So actually, I think I wrote that. I wrote also on the thesis like this works make sense, but it needs to be pushed by projects or by whoever works on 6G standardization to have actually this in place. So there are, I think on one of the last document I read for this, that it was considering this, because of course there are vendors that try to push for it, and there are researchers that push for it because show that actually can simplify, simplify the deployment in one way, but in general simplify everything that has to do with changing the service internally. Because let's say I want to change when the implementation of one function inside the SMF, I need to redeploy the whole SMF. While if that function is just a microservice, I can just redeploy that with a very less impact on the infrastructure or on the architecture.
Do you know if there is I'm sorry for assisting this, do you know if there is some study group or regular side? Because it really seems a lot of work with the mentality of very corporate.
It's going to take a lot of time, that's for sure.